A long wire with uniform linear charge density lambda extends from x equals a to x equals infinity. See the figure below. What is the electric field generated by the wire at the origin? So before we start, you should probably say that the charge density is equal to the total charge divided by the length of the wire, and it is measured in coulombs per meter, units of coulombs per meter. And then have that the electric field is equal to the force divided by the charge, which is in units of newtons per coulomb. Okay, so now that we have this, let's start. So if we draw a wire that has an endpoint and extends to infinity, like a ray on the other end, and we split that into an infinite amount of infinitely small pieces, then we can say that each infinitely small charge at one of those places is equal to the charge density times each infinitely small point. So we're dividing this line up into infinitely many small pieces, and thus the charge of each one of those small pieces is equal to the charge density times the position of each one of those infinitely small ones. It's simply just manipulating this equation here by saying that the charge is equal to the total length times the charge density. So now to move on to the second part, we know that the force is given by Coulomb's constant times the product of the two charges divided by the distance between them squared. Well, we can manipulate this equation to say that the force is equal to the charge times the electric field. So now we can replace that. We're going to say that equal to this. And let's say that this charge is charge 2. Doesn't really matter. So now these two will cancel, and you're left with that the electric field is equal to the Coulomb constant times charge divided by the distance away from that charge square. So from that we can say that the electric field of each little point, and we can probably regard them as point charges because they're so small, is equal to Coulomb constant times the little charge q that the point charge has divided by the distance from that point charge. So now we have this. And from that we can say that the electric field of the whole wire is simply the summation of all of these little electric fields from point charges. And this is simply expressed as the integral of dE. And then we can substitute all of this in for dE. And we're going to set our limits of integration to be from a to infinity, since that's the length of the wire. And then we just write the Coulomb constant, each little charge dq, divided by the distance, the strength of the electric field at that distance squared. And then we can replace each little charge dq with the charge density times each little length of the wire represented by dx. So from that we can say becomes the integral of a to infinity of Coulomb constant times lambda divided by x squared dx. So that's what it becomes. And then from there, since the Coulomb constant and the uniform linear charge density are both constants, we can move them outside the integral. Integral from a to infinity. And this simply becomes 1 over x squared, or it might be easier to integrate if I write it as x to the negative second power dx. And now we just have to integrate this part as normal. this becomes k times, I think it's negative 1 over x, I'm pretty sure. And we're evaluating that from a to infinity. So that's what that integral gave us. Okay, so now we have an integral that we have to evaluate from a to infinity. Now this is a little tricky since we can't just simply plug infinity in. Instead, we're going to replace infinity with t, with a variable t. So what we're going to say is that this becomes the limit as t approaches infinity. Draw a sideways infinity of this. There's a negative sign inside actually. Divided by t. And we're gonna add k lambda divided by a. And this is simply because we're replacing infinity with t, because it's the limit as t approaches infinity. So we're gonna say we're basically evaluating this. Should probably move the negative in front to make it easy. Divided by x, and from a to t, basically, where t is the limit, where this is the limit as t approaches infinity. So we're simply evaluating this expression as t approaches infinity. That's basically what we're doing. And this is positive because we would have a double negative from that. So you have this plugging in t minus, and then you have another negative part of that. So now if we look at this, as t goes to infinity, this would be something like 1 over infinity. So if you suppose that these constants are both 1 or something, this would be negative 1 over infinity, which is pretty darn close to 0. Because as you get closer and add more bigger numbers, you're going to get smaller and smaller decimal points. And this will eventually get closer to 0, so we can just simply assume that this whole part as t approaches to infinity is simply 0 plus this plus the Coulomb constant times the charge density divided by A. And this simply becomes the Coulomb constant times the charge density divided by A. And that is the electric field generated by the wire at the origin. And this electric field will point towards the left, since if you draw this wire, and this will be A, and that will go on towards infinity, your electric field is going to point away, since it is positive. The electric field is positive here, so it's going to be pointing away from the wire. And this is if we're using a positive test charge. So that is a positive test charge. If we use that, the charge would be repelled from the wire. And so the charge would be going towards the left, since that way would be going towards infinity, and is going to be repelled by all of this. So that's that part. So, well, the electric field is given by the Coulomb constant times the linear charge density divided by A, and it is going to be going to the left. Oops, accidentally changed my. It's going to be going to the left, and that is how you would solve this problem here.